Alright, so I would like to take a few moments to discuss the distinction between average rate of change and instantaneous rate of change. Suppose you're traveling in your automobile and you're going on a trip that's 200 miles, say, and let's say you cover this 200-mile trip in 4 hours. Then what would the average rate of change be? And what the rate of change of what? Well, how far you went. How far did you go? You went 200 miles in 4 hours. So your average rate would be your average rate of change would be 50 miles per hour. Your your change in um, position, how much position you moved 200 miles divided by how long you traveled. The change in time. 4 hours passed and you traveled 200 miles. Okay, now, does that mean you were traveling 50 miles per hour the entire 4 hours? No. That's your average speed or velocity over that time interval. Your instantaneous rate of change would be how fast you're traveling at a particular instant during the 4-hour period. Okay, so, and there's really radar. A radar gun will estimate your instantaneous rate of change, but even that is calculating an average rate of change over a very short interval. And that's essentially the idea of instantaneous rate of change is an it you can determine the instantaneous rate of change by calculating the average rate of change over shorter and shorter intervals. Now, to give an example, um, let's talk about a grapefruit. I love grapefruit. It's kind of good to eat. Whether you like sugar and salt on it is up to you. But we throw this grapefruit up, straight up, with an initial velocity of 75 feet per second. It's pretty good initial velocity. It was probably shot upward rather than thrown upward. But the height of this grapefruit t seconds after it's shot straight upward is given by this function. So if we want to find the average velocity of the grapefruit during its ascent, well, we've got to find out when it reached its peak. And the algebra is not the issue here, so I'm going to find out when it reaches its ascent by using the calculator. So we've got 6 plus 75x minus 16x squared. And let's zoom. We'll try zoom fit. See how that works. Oh, that didn't work very well. I must have messed something up in there. 6 plus 75x minus 16x squared. Okay, you know what? Zoom fit did not work very well. Window. Oh, golly. Let's just go 10 seconds. And let's take y from 0 to, oh no, 100 feet by 10s. Alright, that's looking better. So it reaches its ascent. Let's see where that peak is. Second calculate maximum. Left bound, it's somewhere between 2 and 3, it looks like. So left bound 2, right bound 3. Reaches the maximum at 2.343. So, to find the average velocity during the ascent, well, it's going to be how high did it go? 93.890. Well, that is h of 2.343. And the it started at 6 feet. So minus where it started at 6 feet. That's going to be, and we divide that by the 2.343 seconds that it was moving upward. This is really just a slope formula. It's a difference quotient. Okay, so let's see. That's going to be, well, actually, well, I'll use this h of, oh, you know what? I should have stored that value as x. Nice. Okay, so actually, I'm going to store it as, yeah, I'll store it as x now. So I'm going to use some calculator. Y1 of x, that's that 2.343 value, minus, I could just type in 6, but I'm going to type in y1 of 0 for emphasis. Y1 of 0, and I want to put all that parentheses. I forgot to do that. And then we're going to divide that by that x value, 2.343. So divided by x. Remember, it's storing that number in there. So it's about 37.5. About 37.5. What were the units of this average velocity? Well, what are the units of that difference in height? Feet. And what are the units in the difference in time? Second. So 37.5 feet per second. Now, if we want to interpret that graphically, well, here is h of 2.343, and here is h of 0. What we did was this h of 2.343 minus h of 0, that is this right here. That's a delta y, or delta h, technically. Okay, and then we have this as delta t. So what we just found was a slope. Found a secant slope. Red. So the interpretation of average rate of change is a secant slope. Okay, now we could calculate these average rates of change between from 0 seconds to 2 seconds, and that will be the slope of that blue secant, and the average velocity between 1 second time t equals 1 seconds and t equals 3 seconds would be this secant slope, and this average rate of change, average velocity, would be negative because the displacement was negative. It's lower at 4 seconds than it was at 2 seconds. So the average velocity, it makes sense that the average rate of change would be negative in that case. All right, now I'm not going to take the time to actually calculate all of those, but just as an example, the red guy, since I have the red pen open, to find that average velocity, it would just be h of 3 minus h of 1 over the 3, not 3 minus 2, over the 2 seconds, 3 minus 1. That's the slope of this guy. All right, now, let's focus now on how in the world are we going to find exactly how fast the grapefruit, or exactly the rate of change or the velocity at exactly 2 seconds after it was shot up into the air. The velocity is still going to be positive because it was still moving upward. But what is that velocity at that exact point? Well, we're going to zoom in on let's zoom in right there. And let's say we're really, really zoomed in so that we're going to still take a secant slope zoomed in, and I'm going to kind of draw a little picture of what we're looking at. And let's just say that this is t equals 2, and let's say this is t equals 2.001. So let's figure out what, actually, you know what? Start with 2.1. And then we'll do the same thing again, but we'll zoom in even further and we'll say that this was 2.01. And then do the same thing again, but we'll say that this is 2.001. And you can imagine, I suppose, that the smaller you make that little interval, the straighter, the more linear, if you can imagine that, the more linear that function will be. So here's what I'm going to do to model this with the calculator. In Y2, I'm going to actually type in Y1 of 2 plus H. Let's see, we'll make it H. Where's my H? H is right there, above log. Oops, that's an N. H is, my eyes aren't focusing. H, there it is. Minus, let's see, Y1 of, no, you know what, I'm going to make it this way. Y1 of, we'll do this definition. Y1 of A minus Y1 of 2. And I always forget my parentheses. Oh, come on. I need to insert. So Y1 of A minus Y1 of 2. divided by a minus 2. You know what? I'll change that a to x divided by x minus 2. Alright, so now I'm going to go to table, and I'm going to set the table so that it is in ask mode. Okay, now, for x equals 2.1, there's how high there's the height of the grapefruit at 2.1 seconds, and this is the average rate of change, 9.4. That's h of 2.1 minus h of 2 over 2.1 minus 2 at 0.1. And that is 9.4. Now I'll go to 2.01. It's 92 point, it's not quite as high, and notice it was going, the average rate of change on that 100th of a second interval was 10.8, so significantly greater than it was the average rate of change on that. And hopefully you can see that if we take a smaller interval between 2 and a small, the slope is going to be decreasing slightly as you get closer to 2 from the right side. I'm not sure if I... Okay, so h of 2.01 minus h of 2 over 2.01 minus 2. That's 10.84, approximately. These are both approximations. Okay, let's try 2.001. 10.984. So h of 2.001 minus h of 2 over 2.001 minus 2 is 10.984. And I'll go one more, 2.0001. Okay, what does it look like, the average rate of change as we take smaller and smaller intervals between 2 and a number just barely above 2? What does it look like the average rate of change is approaching? It looks like it's approaching 11. So now, so I would say, based on this this information, that it appears that the instantaneous velocity at t equals 2, it appears to be 11. 11 feet per second. Okay, because that's what it looks like these average rates of change are approaching. Now, let's use a limit to actually find the slope of that tangent line, the instantaneous rate of change. We're going to take that h of x minus h of 2 over x minus 2, and we're going to take the limit of that as x approaches 2. And I should technically be using t's instead of x's here. Apologies. Notationally, that's pretty sloppy. Okay, so, well, we've got H of t is 6 plus 75t minus 16t squared. And h of 2 is, let's see, what is h of 2? Let's see, y1 of 2, 92. So minus 92 and over t minus 2. And the limit of this as t approaches 2. So the numerator, we've got the limit as t approaches 2 of t, you know what, I'm going to make this video a little bit shorter by pausing while I do a little algebra. Okay, as it turns out, the algebra required to conclude that this actually is 11, that this limit actually ends up equaling 11, is rather tedious. So rather than go through that, my main goal is to demonstrate the notation of what we're looking at here. We're taking the limit as t approaches 2 of the lit as t approaches 2 of, and these were, remember, how did I, too many things open here. Oh, there we go. Here it is, t of, or h of t minus h of 2, all divided by the t minus 2. I use x on the calculator because I have no choice. So now the other way that we can describe it is a limit as h approaches 0 of h of hopefully I'm going to go back here so where I have more room. We could look at this as the limit as h approaches 0 of h is what we're adding to the 2. So h of 2 plus, oh golly, now I know why I'm going to use a different notation here because I've already got h as my function. My function is my height function. So I'm going to call this delta t. H of 2 plus delta t, a little teeny amount of time added to the 2. So in 2.1 or 2.01 or 2.001, etc., minus h of 2 over that delta t. Delta t in the limit definition that you're familiar with would be h, but I'm not using h again because my function's name is h. So both of these are actually 11, but I'm not going to work them out right now.